Okay, a box of mass 0.5 kilograms is placed on a plane which is inclined at an angle of 40 degrees to the horizontal. The coefficient of friction between the box and the plane is a fifth. The box is kept in equilibrium by a light string which lies in a vertical plane containing a line of greatest slope of the plane. The string makes an angle of not 20 degrees with the plane as shown in the diagram. The box is in limiting equilibrium, there's the important word, and may be modelled as a particle. The tension of the string is T if the box is about to move up the plane. Okay, so part A, find T when it's about to move up the plane. So what we've got is draw it up. Well, I'm going to do much better than that. Okay, there is the box, there is the 40 degrees, there is the tension. Right, what we've got going on here is 0.5 kilograms, so 0.5 there. You've got the weight component, the weight dragging down, which is 0.5 G. You've got the normal reaction, which is pushing back up there, which is R, and it's about to move up the plane for part A, means that in limiting equilibrium, you must have F max opposing that. So first things first, I'm going to componentalize the forces. Okay, so I've got a bit going up there for that, a bit going up there for that, and putting on the information that we've got given, that's 20 degrees just there. So I know that the force T and its component is cos 20, and this bit here is the I'll put that R over there a bit. Force T and its component is sin 20. Okay, and changing that, componentalizing the weight, I've got a bit going down like that and a bit going down like that. Okay, so componentalizing this, well, we always know this is 40 degrees here. So the weight, which is 0.5 G, times by its component, which is cos 40, and the bit going just down here is the weight, which is 0.5 G, times by its component, which is sin 40. Okay, so we're ready to go now, and don't forget the R there. So I'm going to resolve perpendicular to the plane, up is positive, using net forces, because we're in limiting equilibrium, is equal to 0. I end up with the only two positive forces are plus T sin 20, and the opposing one is negative 0.5 G, and it is cos 40, and that is equal to 0. So rearranging this, I've got R is therefore equal to 0.5 G cos 40 and minus T sin 20. And then from that we can get, because we're in limiting equilibrium, that F max is equal to, and coefficient of friction between that and that is a fifth. Okay, so it's a fifth of all of that. So R, 0.5 G cos 40 minus T sin 20. Okay, so that's what F max is. Now I'm going to resolve parallel to the plane, and up is positive, and again net forces is equal to 0. So the only positive one there is my T cos 20, and my two opposing ones is the weight component and the F max. So minus 0.5 G sin 40, and also minus F max, and we know that that is equal to 0. Okay, so I know F max is this, so I'm going to replace that with that, and I I end up with t cos 20 minus 0.5 g sin 40 minus a fifth brackets 0.5 g cos 40 minus t sin 20, and we know that that is equal to 0. Now I'm going to gather the t's up and factorise, so I end up with t open brackets cos 20, and I've got minus a fifth times minus, that gives you a positive. A fifth is 0.2 sin 20. Okay, that gets thrown over to make equals 0.5 g sin 40. That times that gives you 0.1, and it's a minus 0.1 thrown over gives you a positive 0.1 g cos 40. And then finally we end up with t is equal to 0.5 g sin 40 plus 0.1 g cos 40, and that is all divided by cos 20 plus 0.2 sin 20. Okay, so t gives us, and calculator out, fraction button at 0.5 g, so 0.5 times 9.8 times sin 40 times sin 40, close close, we've got plus open 0.1 times 9.8 times cos 40, so cos 40, close close, go down, cos 20, close brackets, plus 0.2 times by sin 20, close brackets, equals, and 3 sig fig gives us 3.87, so 3.87 newtons. Okay,